So, good evening everybody. I'm very happy to be here because A, I love festivals, as you can see from the amount of grace that I have, and also I love data, and I'm actually not 100% a data scientist because I'm a particular type of data scientist. So I work for Yahoo in the computational advertising team, but I'm a research scientist there in the field of computer vision. And for those of you who don't know, what we do as computer vision scientists is that we teach machines how to analyze and understand images. So I'm kind of data scientist, but for a particular type of data, which is visual data. So this is just a slide about me. I don't know if you're interested, but basically this says that I like to find beautiful places around the world where I can do beautiful research. And that's it. I think let's get into the talk. So, computer vision. So, computer vision systems nowadays are able to detect visible, tangible, nameable objects in visual data, such as, for example, faces, cats, etc., guitars, etc. And actually, thanks to deep learning and recent development in machine learning, we are now able to detect this object with an impressive accuracy. And I can tell you that I did my PhD in computer vision, and after years trying to convince machines that birds are not airplanes and so on, after a while it becomes a bit boring and sometimes frustrating. And also, if you think about it, when we look at an image, we don't only see visible, tangible objects, right? Because there is a whole world of invisible properties, intangible, subjective attributes that we necessarily evaluate when we look at an image, but we can't really see their shape. So for example, I can say, this image is beautiful, or this image makes me happy, but I can't really see the shape of a sentiment as I see the shape of the oval of a face, right? And this is very difficult for machines to detect because they are based just on the shapes and the borders of the object. And so, together with colleagues and amazing scientists at Yahoo Labs, we recently started thinking, why can't we build machine vision systems that can automatically detect this kind of subjective properties in visual data? And what I believe is that to do so, machine vision knowledge, as we know it, should open up and borrow techniques and theories from human knowledge that has nothing to do with computer science or computer vision. For example, sociology, philosophy, anthropology, and typically computer scientists are not very good at these kind of humanities. So there's a lot of work to do, but today in this talk I'm going to show you some works that we did at Yahoo Labs, but bridging computer vision with these other disciplines to build effective subjective machine vision systems that can detect some of these properties. So one of the branches of subjective machine vision that have been widely explored by myself and my colleagues is called computational aesthetics. And what we do in computational aesthetics is that we teach computers, machines, to automatically assess the image photographic quality or its beauty degree. It might sound weird, but basically we try to build these machines that can automatically say, oh, this image is beautiful and this image is not beautiful, up to some extent, right? Now, I have a question for you. Is there anyone who knows how a computational aesthetic system might work? Okay, so this is going to be a 2-minute lecture about how these kind of things work. So we're talking about machines, so everything starts with data, right? And in particular, we need to start with training data, with a training set of images annotated by users or professional photographers according to their photographic beauty, to their quality, right? So we have this set of images annotated by humans, so this image is bad, this image is good, etc. And so the idea is that we want to teach this little robot to automatically do the same, so to mimic how humans assign these beauty scores. And to do so, unfortunately, we can't just show an image to the computer and say, hey, this is beautiful, this is not beautiful, because computers can't really see. So computers are a bit dumb when they understand just numbers. And in particular, in this case, they will need numbers that somehow describe some particular properties of the image, in particular compositional properties, photographic properties, color distribution, and so on. So how do we give them those numbers? Well, up to some years ago, what we were doing is that we were designing signal processing algorithm to automatically extract what we call visual features, where visual features are nothing but numbers summarizing automatically some important image properties. So inspired by photographic theory, we were automatically extracting properties such as, for example, color distribution, texture distribution, how much the image follows photographic rules, and so on. And then the machine would automatically evaluate how much the image was following these photographic rules and then assign scores accordingly. Now, what happened 4 years ago in the field of computer vision is that deep learning came into play. Unfortunately, I can't explain you how deep learning works here, but the main idea is that this feature engineering is a bit gone, and basically we give to the machine directly as input the whole image pixel, and the machine will learn automatically by itself what are those numbers that are relevant and discriminative to distinguish between good and bad pictures. End of the lecture. I summarized 10 years of research in one slide, so let's go on to the more festival stuff. So, at Yahoo Labs, we're particularly interested in computational aesthetic, but in particular, we want to focus on a specific type of pictures, which is the domain of portraits, so images with faces only. So ideally, we want to build this computational aesthetic system that can automatically score portraits in terms of beauty. Note that we don't care at all whether the person depicted in the portrait is beautiful or not. We just want to know whether the image composition is beautiful, knowing that there is a person in it. Now, if you followed until now, you might ask yourself, why, if you have already computational aesthetic frameworks out there, you would need one specific for faces? Well, if you know computer vision researchers like me, you might hear them saying very often, an image is worth 1,000 words. We put it everywhere in our presentations, in our dreams, and so on. So what I always say is, I'm not sure if I like this sentence or not, but if an image is worth 1,000 words, then a face image is worth an entire story. Because portraits typically depict humans, and humans come with all their problems of being human, so their history, their lifestyle, their emotions, and so on. And so photographers, when shooting pictures of people, they actually have to follow specific rules, specific photographic rules that reflect the humanity of the subject they depict. And so if portrait photography is a separate branch of photography, then we believed that the computational portrait aesthetic should be a separate branch of computational aesthetics. And so we built this computational portrait aesthetic system by taking a large training set of images annotated by professional photographers in terms of their beauty, and then reducing it to a portrait-only image dataset by running a face detector on it. And then we build on the output of this face detector, and we design visual features that are inspired by portrait photography. This means that we go deep into portrait photography literature and remap each of the rules a photographer follows to shoot good portraits into a computational approach, into a visual features. So we algorithmically describe the image in terms of portrait photography rules. And then we give all this information to our little robot, to our machine learning framework that will learn how to distinguish between good and bad portraits. Now, this is a plot because researcher always needs to show results in terms of numbers. I'm sorry, this might sound boring, but basically what this plot tells us is that this framework works pretty well, and it works better than general computational aesthetic frameworks out there, which justifies the fact that we did all this work to design a specific one for faces. But actually, the nice thing about this framework is that because we carefully designed the features to be interpretable and to map photographic rules, when we look at how the machine behaves when assigning good and bad scores, we can also understand what makes a portrait beautiful from an algorithmic perspective. So for example, there are some features like the sharpness of the landmarks and the sharpness of the face that are positively correlated with portrait beauty. These, if you are a photographer, might not surprise you so much, but remember this is arising from data. The machine had no idea about what it was going to find. And so there are some other features that are negatively related to portrait beauty, such as, for example, the excessive use of colors or the excessive balance in exposure, because we know when you shoot portraits, you should play with the light. And then there is a third group of features that actually does not correlate at all with our target variable, which is portrait beauty. And I can tell you, when things don't work, like in this case, when things don't correlate, this means that we can trash the signal, so it's very frustrating. But in this case, we have a nice message, so I always like to say this, because this tells us that no matter the race, the gender, or the age of the person depicted, if the photographer does a good job in shooting the portrait, then the resulting picture will be beautiful. So, and because we were very happy about what we found in computational aesthetic, we decided to apply on a large scale. So I'd like to show you this work. It's a more applied work that we did in the context of the Flickr photo sharing platform. You might know Flickr. This is a very large photo sharing platform. Is owned by Yahoo, and it has millions of users and billions of pictures. However, what happens in Flickr is exactly this. So only a small portion of Flickr pictures are actually visible and easily accessible for normal users. And this portion of image corresponds to the most popular images, because popular images tend to spread easily around the network, user can retrieve them more easily, and so on. And so as a result, the vast majority of Flickr picture is actually kind of hidden, invisible to the final user. So together with this amazing colleague that I have, we ask ourselves, with the aim of promoting good quality content of our user, we ask ourselves, is popularity a good proxy for quality? Are all the beautiful pictures in Flickr lying on the surface of popularity? And so to answer this question, we ran a crowdsourcing experiment where we ask users to annotate a large number of Flickr pictures in terms of their photographic beauty. And the result of this experiment told us that yes, many popular Flickr pictures are actually very beautiful, but yes, there is a large number of beautiful pictures that are absolutely non-popular. And those are what we call our hidden gems, because those are very high quality pieces of content that nobody can see because they're buried in the sea of non-popular pictures in Flickr. And so with the aim of surfacing these hidden gems and providing this high quality content to Flickr users, we employ a computational aesthetic algorithm. So what we do is that we take a very large data set of Flickr pictures that are absolutely non-popular, so they're all hidden, right? And then we score them in terms of beauty according to a computational aesthetic algorithm, what I described before. And then we rank the pictures according to the predicted beauty, and at the top of this ranking, we will find our hidden gems, because these are supposed to be very beautiful pictures that, however, are hidden because they come from a non-popular pool of pictures, right? Now we could stop here and say, okay, the machine has spoken, let's go and do something else. However, because we can't still trust this type of machine yet, we go back to the crowd. We ask again people to annotate the beauty of this surface gem together with other pictures from Flickr that are from different buckets of popularity. And we were very happy to see these results. So this plot again basically tells us that these automatically surfaced pictures that come from a very non-popular pool of pictures, they are as beautiful or even more beautiful than the most popular Flickr pictures. And we were very happy to see that. And this data, all the data I'm talking about is available online, so just ask me for the link, I forgot to say that. So those are some examples of these surface gems. Those are very beautiful pictures, and these pictures will not be visible to me, to you, and to the Flickr users if we didn't have this kind of algorithm helping us surfacing them. Okay, so again, we saw that this kind of thing can work on a small scale, on a large scale, so we were extremely happy about the kind of things that machine can do. So we decided to push a bit the boundaries of what computer vision is able to do, and we decided to build machines that can explore the even more subjective notion of creativity. So, and to explore this new notion, we focus on a specific online platform called Vine. You might know Vine. Vine is a platform that was acquired by Twitter 3.5 years ago, and that allows users to create and share videos with a maximum length of 6 seconds. And up to now, nothing weird, but actually Vine became a big phenomenon in the visual artist community, because visual artists realized how the 6-second constraint would very much foster their creativity. And so actually artists became famous because of Vine. And Vine became a big phenomenon in the medias, in the computer science community, in the communication science community, and so on. So Vine, since its birth, was linked to the notion of creativity. So after all this introduction, you might think that all Vine videos are creative. And I can tell you that not all Vine videos are creative, and actually 99% look very much like this. And according to our study, then maybe it's not like that. But so when we saw this thing, we said, okay, can we build a machine that can automatically detect creative Vine videos and surface them for the Vine users? And so when we thought about this thing, everybody told us we were crazy, because how can machine estimate these things? And moreover, how do you define creativity, right? Creativity is a notion that has been defined by pretty much every branch of the human knowledge, from philosophy to mathematics to computer science to art. It's endless. So we started studying and we dig into the literature until we found a shared definition of creativity. And we defined something creative as something new, so it has some novel artifacts compared to novel attributes compared to artifacts of the same class, and valuable, so it has some benefit for the final user. And then we take this definition of creativity and we adapt it to the world of micro videos. So we define a creative videos as a video having some artistic novelty, so some unusual patterns in the visual or audio channel of the video stream, and some artistic value. And to define artistic value, we had to bother Mr. Immanuel Kant. And this, I'm not going to get into these details because you will need many more beers, I think. But basically, Kant was the only one providing to computer scientists a definition of artistic value that was divided into mutually exclusive categories and finite categories. So we were very happy because, remember, we have to teach a machine. So we need simple definition and simple things. So again, so now we have defined creativity, but we have to teach this machine how to detect creative videos. And typically machines need data, right? But we had absolutely no training data to train a machine to detect creative videos. So we decided to create our own training data. So we designed this crowdsourcing experiment where we ask crowdsourcing contributors to annotate 4,000 videos, Vine videos, in terms of their creativity. And again, this data is available, and I can tell you, not because I did it, but this is very high quality data, not only because we carefully designed the experiment and did so many pilots and asked users, etc., to verify that we were collecting the right annotation, but also because we can quantify how much the quality of the annotation, and we have a very high agreement on a large set of videos, so this should be good data. And then again, we have to teach this machine how to detect creative videos, but we can't show to the computer the videos because it won't understand anything. So we have to provide them numbers again. And in particular, in this case, we want these numbers to reflect creative traits of the videos. And so we design, using signal processing technique, these visual features that would automatically expose artistic value and artistic novelty properties. So for example, for artistic value, we are inspired by literature from filmmaking and from photography to design features that can expose some parts of the artistic value, and then to expose video novelty. Basically what we do is that we detect how much the visual or the audio pattern of the video deviate from the general patterns of the video in the Vine stream. Okay, so now we have all the elements that we need to feed the machine and make the machine detect creative versus non-creative videos. And at this point you might think, okay, this can't work, right? Because machine can't see this kind of things. So you might be as surprised as we were when we saw that for a very clean part of our data set, this system is able to detect creative videos with 80% of accuracy, which is pretty high for a computer vision task. And again, because we design features to be interpretable and to expose creative traits, we can also understand what makes a video creative from an algorithmic perspective. Okay, and so as last part of this talk, I'd like to show you a work that we recently started with an amazing team of researchers from all around the world. And this work explored the even more subjective notion of sentiment. What is more subjective than sentiment? Think about love. If I was asking you to put love into pictures, then probably each of you would assign different visual concepts to this emotion. And this is because emotion perception is very subjective. And it very much depends on our day, how our context, our cultural background, etc., etc. And I have to admit that myself and my computer vision colleagues, we've been trying in the recent years to automatically detect sentiment into pictures, but the error that we keep doing is that we don't count for how much subjective sentiment can be. We imagine that all users, all people are the same, but actually sentiment varies so much according to people's life. And so when we look into psychology literature, one of the main thing that we found is that one of the most important factor influencing our emotion perception is actually the cultural background where we grew up. And so we team up with this researcher from Columbia University, IBM, EPFL, and a number of other institutions. And we built this framework that allows us and the whole community to study the impact of culture in visual emotion perception. And so the main aim of this project is to answer, up to some extent, with an algorithmic solution, this question. So how similar are emotions across culture? How, for example, happiness is different from if I think about happiness in a picture, or if my Chinese colleague thinks about happiness, right? So we are very much interested in this. We don't have the answer yet, so I won't provide you an answer, but I'm going to show you some of the experiments that we did towards the aim of answering this question. So obviously we want to perform computational approach. So first thing is to get data, and so the first thing that we did was to collect this large data set that we call multilingual visual sentiment ontology, and it's about more than 7 million Flickr pictures. And these pictures come from users in Flickr from 12 different languages. And each picture is annotated with the language of the user that uploaded the picture, a positive, negative sentiment value, and some emotion keywords that tend to occur very much with the image metadata. So to collect this data, I have to go very quick here because it was a massive effort for the 6 of us. But basically, we had to design our ad hoc pipeline because no one before has ever done this thing, so we had to do it ourselves. So everything started with the Plachik wheel of emotion. Plachik was a psychologist, and he designed this wheel of emotion that is basically 24 emotion keywords organized according to some psychological attributes. So we take the 24 emotion keywords and we translate them into 12 different languages, asking friends and parents, etc., to correctly, native speaker basically, to correctly translate from English. And then we query Flickr with this bunch of keywords, we pull all the metadata returning from the images, and we polish this metadata with the hell out of natural language processing, crowdsourcing, visual analysis, etc. And at the end, we have this reliable data set called the multilingual visual sentiment ontology. Now, what do we do with this? We want to answer, again, this question, which is understanding how culture perceives visual emotions in online image data. And so the first experiment was actually to perform a very basic analysis of the data that we had. So the first experiment was to actually analyze how emotion keywords tend to be attached by different culture in their image collections, right? So this is boring. I'm not going to get into these details. It's just about how we compute this metric. This is the interesting part. So each of these squares, basically the darker the square, the higher the probability that one of these populations in Flickr mentions one of these keywords in their image collection. Now, this looks very nice. I could infer so many things from this plot. However, because we are just at the beginning, we have to verify these findings with psychologists and with psychology literature. But the main idea that we see here is that this distribution of emotion for different languages is very different, which justifies the fact that we did all this. So different languages tend to assign different emotions in online images, right? And then we did the same with sentiment, and we compute the average sentiment of the metadata attached to the pictures from each population in Flickr. And again, here I'm very happy to see that Italians are among the happiest population in Flickr, because I'm half Italian, but we can't really infer this as a general rule. So we are actually refining this analysis to see what we can do with this. Okay, as a last experiment, I'd like to show you some more a bit more complex experiment that we did using this data set, and it's about comparing sentiment models for different cultures. So here we want to understand basically how each language assigns a positive, negative sentiment to each image. So what we do is that we take the 6 biggest languages in our data set, and then for each language we design a language-specific sentiment predictor that basically is able to assign a positive, negative sentiment to the images of that specific language. Up to now it's a bit boring, but the funny part is when we try to mix these predictors. So for example, I try to predict the sentiment of Italian images using the sentiment detector trained on Chinese images, right? So this is what we do. Okay, so this is how we design the language-specific sentiment detectors. I'm not going to get into this monster. This is a deep neural network. But the idea is that for each language, say German, we take all the images from that languages, and then we have an annotation that is a positive, negative sentiment. So we can feed this neural network directly with the pixels of that image, and the neural network will automatically detect positive, negative sentiment for each of the languages. Those are the language-specific results. That's so interesting. It works very well. It works better than random, but we have nothing to compare with because this is the first work of its kind. But the interesting part comes when we perform crosslingual sentiment prediction. So what we do is that we have our language-specific sentiment detector. So we try to predict the sentiment of a language from the sentiment detector trained on other languages, right? And the idea is that if cross-lingual prediction performs very well for two languages, we can assume that this is because the underlying data distribution is very similar. And this is because the two languages tend to associate positive and negative sentiment with the same visual concept. So they are kind of more similar in expressing visual emotions in online image collections. And so these are the results. They're very ugly, grouped by language, but I'm going to show you some better looking results. So these are the results of the cross-lingual prediction. So immediately what we can see here is that Chinese sentiment is the sentiment that is most difficult to predict from sentiment detectors trained on other languages. And this is because basically Chinese is the only Eastern culture in our data set. We assume so. And the other pattern that we see is that for Latin languages such as French, Italian, and Spanish, cross-lingual prediction works much better. So it's very easy to predict the sentiment of Spanish images given detectors trained on Italian images. Yes, I'm almost done. And so this is just the same representation of what I said before. And here is an example, qualitative examples. I like it. So, for example, this image is tagged with costumi tradizionali, which is traditional customs, which is, in Italian is a very positive concept. But when we try to predict the sentiment of this image with the detector trained on German images, then it will assign a negative score, a negative sentiment. So this tells you, that there is a lot of work to do in understanding how different languages assign sentiment in online images. And these findings and many other findings were actually possible. It collapsed. No, were actually possible because we carefully design our features, our experiments, and our algorithms to be interpretable. Because this is the only way for us to understand how, from an algorithmic perspective, how we humans perceive online image data. And we might also go back to the scientists of the disciplines, that's actually where we borrow from, and provide them with our findings and see if we can start actually a loop of collaboration and interdisciplinary collaboration with these other disciplines. And with that, I conclude. I have to thank all these people. Every time I have to squeeze the picture more because there are so many people that help me with my work and I want to thank them all. And I thank you very much. And if you have a question, I'll be happy to listen to them. Thank you.